in the last module, we had began with the single equation estimation methods for simultaneous equation models. As the first of these methods, we had looked at the indirect least squares. We saw that the problem with the indirect least squares is that although it is easy to do, very often it cannot be applied because it requires that the equation be exactly identified before we can apply the method. So, if an equation is over identified, then the indirect least squares would lead to multiple estimates of the parameters, which can be very confusing. What we will do today is to look at a different method, which is referred to as the two-stage least squares method. The two-stage least square method has an advantage in the sense that it does not require that the equation be exactly identified. Even for over identified equations, we can apply the method, and hence the two-stage least square methods are more popular. We will also look at what is referred to as an instrumental variable technique, and we will see that both the two-stage least squares and the indirect least squares can be taken as special cases of the instrumental variable technique. So, when we look at two-stage least square methods of estimation, let us go back and look at the jth equation. So, we have y j is y j prime beta j star plus x j prime y j gamma j star plus u j, where we know that there are g endogenous variables which comprises of the small y j along with the capital Y j. These are the endogenous variables. So, capital Y j actually comprises of g j minus 1 endogenous variables, and x j are the k j exogenous variables. The problem is that the y j's on the right hand side are correlated with the u j's, and hence ordinary least squares cannot be applied. This is, we have seen previously that the endogenous variables would be correlated to the u j's, and hence OLS cannot be applied. So, what do you do? Let us go back and look at the structural and reduced form equations very quickly. So, we have B y plus gamma x is equal to u. This is the structural model, and this goes to the reduced form model as y is equal to minus B inverse gamma x plus B inverse u. We can take this inverse because B is a non-singular matrix, G by G non-singular matrix, and we have this equal to pi x plus V. So, we write pi as minus B inverse gamma. Now, since our concern in this case is primarily with the y j variables that are in the jth equation, right hand side of it, so we need to replace these y j's. So, what do? We pick only those y j's from the reduced form. So, we have y is equal to pi x plus v. Some of these y's would actually be the y j's that we have in the jth equation. So, we only pick out those y j's, and now we can write this y j's as equal to pi j x plus v j. So, correspondingly we also pick up the pi j's. So, we have only this g j minus variables picked up from the whole reduced form, and we have the equation y j is equal to pi j x plus v j. Notice something about this new equation. In this new equation, the right hand side consists only of the x's. You do not have any y's here, and hence we can apply the ordinary least squares equations here. The ordinary least square would lead to pi j hat being equal to y j x prime x x prime inverse. So, we get an estimate of the pi j's. Now, what we do is go back to the original jth equation. and replace the yj in the jth equation by the predicted value yj hat, which is pi j hat into x. So, instead of using the original y's, we use the yj hats, and this changes the regression model to yj, small yj is equal to yj hat prime beta j star plus x j prime gamma j star plus uj. So, what we have is simply the previous model with the yj replaced by the yj hats, and we will call this equation star. Our claim is that unlike yj and uj, yj hat and uj are uncorrelated, and we will show how and why this happens. Look at n inverse yj hat uj, and we substitute yj hat here by what we have for yj, that is pi j hat x, and if we write out pi j hat, it becomes yj x prime x x prime inverse x into uj. And now, let us look at the three terms here. The first term yj x prime and the second term x x prime inverse actually leads us to pi j, whereas n inverse x uj, this will be going to 0 because x and uj's are uncorrelated to each other. So, what we have is pi j into 0, which is equal to 0, and hence asymptotically this yj hat and uj are uncorrelated to each other, and hence if we have a reasonably large sample, we can use the ordinary least squares on star. This leads us to the 2SLS estimator. This is given by beta j hat prime gamma j hat. This is yj hat into yj hat prime y prime x j prime x j yj prime and x j prime. Now, if you look at this whole setup here, yj hat yj star leads to the 2SLS estimator beta j hat gamma j hat, which is given by this form. And just notice that this is in terms of the predicted values of y. The dispersion of this would be given by the usual dispersion, that is the inverse of the first term here. So, it's as you get in usual regression, where you have the estimated as x prime x inverse x prime y, and the dispersion comes out to be sigma square x prime x inverse. The same rule applies here, and you get the dispersion. Only thing is that sigma square needs to be estimated, and it is estimated as sigma hat square, as we will define this as a residual sort of. So, it is E prime E by the degrees of freedom. Now, let us look at some simplification, because what we did was we did two least squares. First of all, the least squares on the reduced form to get predicted values of yj's, and then substituting the yj's in the original equation, we did another least square which led to the actual two-stage least square estimators of beta j gamma j. So, we did it in two forms, but can we do it more simply without going into two regressions? Notice that you have yj is equal to yj hat plus bj hat. What is bj hat? Bj hat is yj minus yj hat, which we generally call the residuals. And it is easy to see that if you write this bj hat as yj minus yj hat, then we have x into bj hat is equal to 0. This is because you substitute vj hat, which is yj minus yj hat prime, and you have, after some simplification, both terms coming out as x yj prime. So, they cancel each other and we get 0. So, x is as always uncorrelated to the residuals. and this leads to some other results like yj hat bj hat. Now, mind you, yj hat is pi j hat x, and therefore, x being uncorrelated to vj hat, this is also going to be equal to 0. So, the 2 SLS can in fact be written in terms of the original variables. How? Remember, the first term was yj hat prime. So, if you simplify this in terms of the original variables, yj, one of the yj hat can be first written as yj minus vj hat, and now we have vj hat and yj hat are uncorrelated. Therefore, that term actually is 0. So, we have yj hat into yj, and now replace the yj hat, estimated value of it, and you get the whole thing in terms of only the yj's and the x we had as the original data. Similarly, if you look at xj yj hat, this reduces to xj yj prime. So, the whole thing can now be written in terms of the original variables in this manner, and hence we do not really, if you know this final result, we do not really need to go back and do the 2-stage least squares. We do not really need to get the predicted values of yj's. We can write the whole thing in terms of the original variables themselves. Now, let us turn to what is referred to as the instrumental variable technique. You have learnt of in the instrumental variable technique in other courses, but let us see how instrumental variable techniques can be identified with both the 2-stage least squares that we saw today and the indirect least squares that we saw in the last module. Before that, let us very quickly go through what is an instrumental variable. So, we have the model yj, the jth equation, and we write this as zj prime delta j plus uj. We will call this 1. Of course, zj now is yj and xj. These are the endogenous and exogenous variables which explains the small yj, and this is the n by gj plus kj minus 1 dimensional matrix. And of course, we define the del j's as the deltas would be the beta j's and the gamma j's. Those are the parameters in the jth equation, and it is going to be of dimension gj minus 1 plus kj, gj minus 1 for beta j and kj for gamma j. So, using the least squares, the normal equations usually are zj yj is equal to zj prime delta j. But the problem with this is that we cannot use this, since the zj's contain y's which would be correlated with the error. So, we have inconsistent least square estimator. We will show this. So, delta j hat zj prime inverse zj yj, that is the least square estimator, and since n inverse yj uj does not tend to 0, it tends to some constant cj being correlated to each other. This delta j hat would not tend to delta, it will tend to something like delta j plus sigma inverse cj 0 vector, which is not going to be 0, and hence is not going to be tending to delta j, and hence the estimator is inconsistent. That was the problem we had, and that is the reason we had to do the ILS or the 2 SLS. So, usual least square estimator for the simultaneous equation model does not hold. So, question is, can we find a consistent estimator of delta j? We need to find a matrix zj star which has to have two properties. Firstly, it has to be highly correlated to the original zj's, that is, this tends to some positive definite matrix G. They should be as highly correlated as possible, because we will be using them as a surrogate for the original zj's. On the other hand, this zj star should be uncorrelated to uj, unlike zj is correlated to uj. So, we would expect that at least for a size large sample size, zj star and uj star would be uncorrelated. Then what we do is, we pre-multiply the model by n inverse Zj star, and this is what we get. And notice that the second term on the right hand side is going to go to 0, and therefore, we can estimate delta j hat as Zj star Zj prime inverse Zj star Yj, which we will call the IV estimator. Now, what is good about the IV estimator is that if you look at delta j IV, you can write this as delta j plus again bring in n inverse on either side, and you will see that the last term goes to 0, and therefore, what you have is delta j plus g inverse, which would be the term previous to it, into 0, and hence this would be tending to delta j. This is because Zj and Uj are uncorrelated to each other. So, the IV estimator is going to be a consistent estimator. One thing about instrumental variables that is very often a mistake that is very often made is that we do not actually replace Zj in the model, we only pre-multiply the model by n inverse Zj prime. So, the Zj in the model stays. If you look at the estimator, it is not Zj star prime, it is Zj star Zj prime. So, the Zj is there, and we only use the instrument as part of the replacement of Zj. So, you should be careful when you work this out practically. Very often what you do is you remove the Zj completely and use the Zj star, which is going to be wrong. Let us have a look at the 2SLS and the IV estimators. The 2SLS can be written as beta j hat gamma j hat, which is in the final form Zj star Zj prime inverse Zj star Yj, where you have your Zj prime, that is Yj xj, replaced by Zj star, which is Yj hat xj. So, the Zj in has y and Zj star has Yj hat replacing y. X remains the same in both cases, and as we know that since Yj hat is uncorrelated to Uj, unlike Zj, Zj star would be uncorrelated to the Uj's as well. As for the IV estimator and the ILS estimator, remember the ILS estimator was this form, and in this case what we do is we have our Zj as Yj xj, but now we replace the Yj's by xjm. Remember, xjm are the excluded exogenous variables. So, we replace the Yj's by the corresponding excluded exogenous variables. So, the ILS estimator that we did in the last module can also be looked upon as an IV estimator, and since xj's are uncorrelated, so xjm's are also uncorrelated to the errors, this estimator is also going to be a consistent estimator. So, both the ILS and the 2SLS estimators are consistent. A comparison from model, we have Zj as Yj xj, where Yj has Gj minus 1 columns. These are the columns which creates a problem, because these are correlated to the errors. On the other hand, in the 2SLS, we replace the Yj's by the Yj hats, where again Yj hat has Gj minus 1 columns. So, now we have the Yj hats independent of the errors, and hence the estimator becomes consistent. For the ILS, we actually use xjm as a replacement for the Yj's. These are the exogenous variables, and hence again are uncorrelated to the errors, and hence again leads to consistent estimators. So, in one case we replace by Yj hat, in the other case we replace by xjm. The only difference is that xjm has k minus kj columns, and therefore, for the ILS it is necessary that k minus kj must be equal to Gj minus 1, so that it can replace the Yj's. And remember that this is the condition for exact identifiability. So, as we have mentioned in the last module, the ILS can only be used when we have exactly identified equation. But the 2SLS, since we are replacing Yj by Yj hat, which has the same dimensions, it does not require the condition of exact identifiability, and hence you can apply the 2SLS whether or not the equation is exactly identified or not. It can be over identified. So, as long as it is not under identified, you can use the 2SLS method. In today's module, we discussed the two-stage least squares. We saw that we do it in 2 steps. At the first step, we actually estimate the endogenous variables that are on the right hand side of the equation, that is, which acts as the regressors in the equation. And at the second stage, we replace this estimated or predicted endogenous variables in the model, and then we estimate the parameters from the model. We saw that this is a advantage over the ILS estimator in that it does not require that the equation be exactly identified. We also saw that both the indirect least square method and the two-stage least square methods can be looked upon as instrumental variable methods, where the Yj's that are creating the problem of because of the relationship with the errors can be replaced either by the Yj hats as in the two-stage least squares, or by the excluded exogenous variables as in the ILS method, and this leads to consistent estimators. In subsequent modules, we will be looking at a few more of the single equation systems.